Morning, everyone. Welcome to the fourth and final day of the Goby3 course. Um, Appreciate you all sticking with me here. And again, today's lecture will be recorded, posted online for folks to watch afterwards, be publicly available. I also have pushed my solutions to yesterday's homework to a branch post homework 3, following the same naming scheme I've been using all week. So if you want to take a look at what I did for those, you can just check out that branch. Everything will be right there. So today we'll also have office hours again, one final time. So it's your last chance to ask me questions about any of the homework. And I would encourage you to ask me questions today if you have them, because I will have to go back to my normal job next week. So I'll be much less responsive on anything after today. So revisiting this triangle of communication, autonomy, and sensing. Today's focus is on that last point of sensing. And again, while Goby is focused really on communications, to build a complete robot system, we also need to provide support for these other pieces. So the focus is going to be really on how Goby can make integrating sensors and sensing into your system easier and play well with the rest of the vehicle system. So what are we looking at for sensors in marine robotics? And there's a whole wide range of oceanographic sensors, of which this is only a short list. Like physical sensors measure things like CTD, water velocity, ADCP, magnetometers. So physical oceanographers. Data types, we have chemical sensors like pH, CO2, nutrients, biological sensors, DNA, cytometers. We have lots of different types of imagery. We have like actual cameras, seafloor cameras, as well as imaging in the water column, like this Mesobot project that Hui's working on to track creatures in the water column. And then finally, we have sort of the whole class of remote sensing, especially with relates to sonars, AUVs. So that could be seafloor mapping, or hull inspection, that kind of thing. So there's a pretty wide range of different types of sensors. And while not all of these are really deployed on AUVs regularly, there's sort of increasing miniaturization, as well as reduced power usage. A lot of these sensors means the choices are increasing. So you may have a lot of different things you want to put on your vehicle. And then so looking at oceanographic sensors and sensors in general from a software viewpoint, there's some common themes that I've seen. Many of them are serial based. We're finally slowly getting away from that, perhaps in some cases, but still pretty common to see serial interfaces and a whole range of what I'll call ad hoc protocols developed by various vendors with little to no standardization on protocols. They often have what I'll call quirky state machines. You're not entirely sure what state the sensor's in. Sometimes you have to query it several times to get it to respond correctly. And these sensors are often quite expensive. So unlike perhaps a GPS or the Internet of Things sensors you can buy for, $50 or so, you're talking thousands of dollars. So having extras just for software development use is often challenging or impractical. So we often need to develop our code against a simulator, test it against simulators, and use that as a proxy until we can briefly use the real sensor to do the final testing before deployment. So we'll look at that model here in today's lecture, as well as in the homework, of developing a simulator for a sensor based off the interface, developing the driver for that sensor based off the simulator, and then that's a starting place. You've done a lot of the heavy lifting for when you actually have access to the real sensor. So what does Goby provide to make sensor integration easier? So there's a handful of sort of related things. The first that we'll talk about is a suite of IO threads that we can extend for new protocols. And what exists already in Goby, we have serial, UDP, TCP, CAN bus, P2Ys, or virtual serial ports. It's a general use for that. And then in terms of Delimiter protocols, we have line-based, so something like carriage return new line-based ASCII protocols. There's a binary Mavlink protocol in there, and it's designed, as we'll see in a bit, to be quite easy to add new wire protocols. It's pretty much just implementing a single read method to do so. Then there's this Goby GPS application that I talked about the first day of it, which is a client for GPSD, the Linux GPS daemon. We'll look at that a bit. And then Goby will show how Goby can provide straightforward integration with Boost State Chart if you want to track the life cycle of your sensor states. And that'll be the last piece of today's lecture in pairing with sensor simulation, and some best practice suggestions for that. Okay, so now we got those preliminaries. Let's switch back over to the code. So the first piece I wanted to talk about in Goby are the I/O threads. So let's say we have a serial-based sensor, which is pretty common, and I've got one right here in my office, which is a GPS. Nice and simple starting point. So the GPS uses NMEA 0183. So if I just connect to that here using Picocom, connect to USB 0, which is the serial port that this is on, at 4800 baud. And you see, all of you will be familiar with your standard GPS sentences. So nothing new there, but it's a good starting point. So let's get this into Goby. So what we'll do is we'll create a new application, copying it from the patterns directory as we've been doing all week. So we go src bin patterns. We can copy the multi-thread pattern, and we'll just put this in a directory called GPS. And as we've gotten used to, especially if you've been doing homeworks, we go into GPS, open up all these files. We got to change the class names. We'll just call these GPS driver. And then the CMake list, change the name of the built binary. Call it Goby3 course GPS driver. And the config file. Let's call this. Nothing new there. And inform the parent CMake list that we're going to want to build this directory called GPS. So the other thing I'll do is there's a fair amount of example code in this multi-thread template or pattern. So I'm just going to clear out all that because we won't be using it, and we won't be using the loop method either. So just delete all these extra sub-thread examples. And we don't need loops, so we'll take away this. We're not going to launch these example threads yet. We'll add those back what we need, and then everything else here is gone. So really clean that up a good bit. Now we just have a basic multi-thread application and a constructor. Okay, so before we add anything more to this code, let's take a look at the available I/O threads that are in Goby. So these are all in Goby3 src middleware in the I/O directory. And so if I just take a look at all the files in here, we've got a number that are packet-based, like CAN bus has its own protocol for both the transport and packet definition. The UDP is packet-based, point-to-pointer, one-to-many. And then we've got ones that are line-based. So this is end-of-line delimited in some fashion. So most common is like carriage return new line or new line, but it could be any kind of character or string that delimits the end of the line, or any kind of regex technically. So pseudo-terminal, serial, TCP client and server, and then the Mavlink stuff for serial and UDP. And then in detail, there are these base classes that we'll look at in a minute. This is how you can add our own new protocols based on the existing transport options, TCP, TTY, serial, CAN, UDP. Okay, so all the All of the IO threads inherit from this IO thread class, which is fully qualified. It's Goby middleware. IO detail, IO thread. And this thread does a couple of things. It's going to subscribe to the outgoing data. So by outgoing, I mean from Goby to the sensor. And the message it uses is this protobuf IO data, which we'll look a bit more at in a minute. And the group is a line out group. And this group is actually a template parameter. So this is not a fixed group. You can determine what you define your own groups that you're going to use and pass them in. So let's actually look at the header for that. So it's in detail IO interface. So this, scroll up to the top here. So here's our IO thread class. And its template parameters, the first two that I will look at are the line in and out groups. So these are how we pass in the actual groups that are used to publish and subscribe between this IO thread and your application. So the other thing the base class does for us is it handles the sync between Boost ASIO, which is how all these are actually implemented. That's how we're talking to serial, UDP, TCP, etc., and the Goby interthread transporter. So that's sort of a nice piece that you don't have to deal with. Every time you get a message in, the two are synchronized, so that you can immediately publish the data that come in off the serial port, and you can immediately write out any data that comes in that you subscribed for. And then we have some amount of uniform error handling, and this is it's published to the protobuf IO status type and on the line in group. So that's these are the two groups that out to the sensor, into Goby. And these kind of errors like read write errors, or if the socket can't be opened, we'll look at that as well. So then the implementers of this class need to provide three virtual methods. We've got here there. These three. We got open socket, async read, and async write. So open socket, as the name suggests, is the implementation needs to, I'll say, try to open the socket. And if it fails, it can inform the base class of that. And then the async write read, this is going to be start an asynchronous read from the socket. And this needs to return a message, whatever that means in context of the protocol. So in the case of like the line-based situation, that'll be a line from the previous delimiter through to the next delimiter. So like in the case of serial protocol, it's a single GPS sentence line. And then the async write, I'm sure you're all shocked to find, is to start an asynchronous write to the socket. And this one's actually easier because most of the time you can just use this free function that's provided in Goby called basic async write. And you can use that most of the time because the assumption is that the IO data packets have the delimiters in them or whatever, so they're already ready to go, and you can just write them out to the socket or serial port. So given that, let's take a look at the implementation for serial, because that's the one we're going to use first. And we'll look at the line-based, so an IO line-based serial is the one we'll look at. So the class diagram for that looks like this. So you've got your IO thread-based class that we've been talking about, which does a whole bunch of stuff for you, and then we have to implement open socket, async read, async write, and then there's this sort of first level implementation for serial. This detail serial thread, which does the async write and open socket for us. So it opens the serial port and can write to it. And also publish some status information about the serial port, including the DTR and RTS levels and things like that. And so then the last thing that's all we really have to implement for the line-based serial thread is the async read function. So if you look at the line-based serial thread, we end up having just a constructor, destructor, and async read method. And the async read basically calls boost async read until. So read until we match this end of line matcher is a regex matcher. So it basically, when you want to implement a new protocol, all you need to do is implement this single function for whatever your end of line. Well, end of line is covered by this one, but say your framing protocol, like I have to read 2 bytes. Those are the size, then read the size, read the checksum, that sort of thing you would implement here in a single method. So, and then once you have if you have success reading, you just pass that over to the base class and it deals with everything else. Start a new read. And if you had an error, you can pass that also to base class and it'll handle it uniformly across all the IO threads. So now we've got a glimpse into how this is implemented, and perhaps you can pretty easily take this and turn it into for your own new serial protocol that you've got. We can flip our focus now on how to use these classes. So switch to becoming a user of the IO threads. So going back to day 2's lecture, so each IO thread is just a Goby thread, so we can just launch that in a multi-thread application. And by default, the Goby thread used is simple thread, and that's, as you recall, the 3-layer inter-thread, inter-process, inter-vehicle hierarchy that we've been looking at this week. So if we look at how we're going to launch this, we're just going to basically run it as a thread within our driver, and we'll communicate it between it by publishing to the line out group and subscribing to the line in group. So minimally, there's several messages that can go over each of these groups, but the core one is this protobuf type IO data. And that's what actually contains the bytes we want to send to or receive from the serial port. So in order to use this, these groups are template parameters, so we need to actually create real instantiations of those. So if we go back into Goby3 course, src lib, if you recall, we're keeping all our groups in this groups header. So we'll create a couple of new groups here for talking to our serial driver, serial thread. So we'll call the incoming one GPS in, not surprisingly, and then the analogous one will be GPS out. So now we have some groups. We can go back to our app, and we need to include the header for the line-based serial thread. We need to we'll use a type def to clean things up a little bit. So we'll call our serial thread is going to be the Goby middleware IO serial thread line based. And then the template parameters are the line in group and the out group we want to use. So we want to use Goby3 course groups GPS in for the incoming data, and we'll use the analogous GPS out for the outgoing data. So now over here, we've sort of changed this to be line in group. We've made that GPS in, GPS out. Now that we've actually instantiated this. And just check that this builds while we keep going. Make sure I didn't mess anything up. And then the last thing we need to do is we need to configure this thread. It needs to know what the serial port is and what the baud we want to connect that is. So that's done using a proto message as usual in the serial config.proto. So let's import that. It's in Goby middleware protobuf serial config. And then we'll create a field in our GPS driver for the configuration of that. So we'll have a required field because our code can't do anything without us configuring a serial port. And we'll just call that serial. I just used index 10 to give me a little bit more room if I wanted to add something earlier, but it's not necessary. I could do 3 here as well. So then we go back to our base class here, our application rather, and we need to actually launch our thread. So we've typed deft it, but we want to launch it. So to do that, we do launch thread, serial thread, and then to pass the configuration, I do CFG to access the application configuration, and then serial, which is this new serial field I added just a minute ago. And so then that should be ready to go once it compiles. So this will run, but we don't actually have subscription or publication here yet. So we'll just take a look at this and then we'll add those in. Okay, so that's built. We go over here, we run our Goby3, and we can run our little driver here, passing to the command line the port that we want to connect to. So this is dev tty USB 0, which is where my GPS was or is, and a baud is 4800. And I'll do debug to verbosity so you can see what's going on. So if I open this up, you can see that the serial thread has its own glog stream, and you can see it streaming into all these messages, which is great, except we can't actually use them yet because we need to subscribe to the GPS in group. So let's do that now. And then I can do inter-thread. I should call from the first day or on the inter-thread layer inside this process. This is called subscribe. The group we want to subscribe to, which is this GPS in, get data from the serial thread. And then the type I want to subscribe to is going to go in the Lambda. So that's going to be this Goby middleware protobuf IO data. So this IO data message. And then when I get that, right now we'll just write out a debug sentence. I'll put it in this glog channel or group called main and say received 01. Okay, so we subscribe to this GPSN group, and then we'll just write it out to glog. Of course, at this point, you can do what you need to with the data. You can parse it and then republish a parse message would be a pretty common situation, or whatever you need your GPS message for. So now that that's built, we go back over here and run this again, and you can see we're now getting all of the serial lines over on our main thread as expected. And the IO data message is really simple, especially when using a serial. It just has one field that's in use called data, and that's just a string, or rather bytes, technically, in protobuf language, because you can use this for both ASCII and binary protocols. All right, so now that we've got that, let's take a look at some of the other stuff that we can get over off the serial thread. So if I unplug the GPS, I'm going to physically unplug it. Not surprising, you get this read failure message, and then it tries to reopen it, and I get this init failure. There's no such file or directory. And perhaps we want to get that information over to our main thread as well. So let's do that. I'll just add another glog stream so that it's easy to see. And then we're going to subscribe to the same group, because it's always the GPS in and out group here. So oops, GPS in. But now we're going to subscribe to the IO status message instead. So the IO status is where it provides, is the port open, closed, error, things like that. Okay, and then when we'll get that, we'll just also write this out. So then once you've got this status, you could check the state of the port, and if you've got some connection failure, then you could decide what you're going to do. Are you going to recover your vehicle? Are you going to decide to continue on anyways? If you have the ability to power cycle that port, you could choose to do that. All kinds of stuff that you could potentially decide to do while in the event of some kind of failure. So now if that's built, we can open this here again, and now you can see I'm receiving my critical failure that it can't open this serial port because there's no such file directory. And if I plug it back in, so it retries on a back off window. So then you get IO link open on the status, and okay, now we've got data again. So there's an automatic retry that increases the time between reopening the port in the event of successive failures. Caps out at a few minutes, I think, between tries. Okay, so that's kind of the core of using the serial thread, the line-based serial thread. And we can look at the rest of the interfaces graphically in that GPS driver. So we're going to create a little bit of a stub deployment file. Right now, our deployment is going to just include this GPS driver. So let's create a GPS deployment YAML. And I'll just put it in today's lecture directory for lack of a better place to put it. And so we'll call this deployment the GPS deployment. And we'll have one platform, and we'll name it the exciting name of vehicle. If you had a real deployment, you'd name your vehicles whatever you're naming them. And then interfaces files that we're going to add to this deployment is just the single GPS driver. So now we've got this deployment. We can build a figure for it by adding to the root level CMake list, which is where I'm putting these. They don't have to be in the root level one, but that's where I've been keeping them. In this section under export Goby interfaces, we've got all these generate interfaces figures. So we're just going to create a new interface figure. So what we're doing is we're passing it the deployment file I just created. This variable is filled with all of the output interfaces definitions built by the Goby Clang tool, and I'll generate this SVG image GPS interfaces. And this is any additional command line flags to Goby Clang tool. So I've got that, save that, and then I can build this again, and it's going to generate me this SVG, which I can open, just in build, share interfaces. Okay, so here's the figure that it built for us, and this is going to show the incoming in other words, the subscriptions. So here's our outgoing data if we were sending data to the GPS, which we're currently not doing, or commands. So serial command here is set DTR high or low, set RTS high or low, send a break across the serial port. And then the publications by the serial thread are the IO data, which we subscribe to in our main thread, as well as the IO status, which is T4. We subscribe to that in our main thread. There's also a serial status that's published, and the thread state. Thread state is basically published once when when the thread is fully ready and ready for subscriptions, essentially. So this can be useful in some cases. It's often better to just wait for the IO link to be open, which can be determined by the IO status message. And then the serial status, this one is just a response to the command. Essentially, if you change RTS, it acknowledges that RTS is high, for example, if you set it to high. So you can read the those two pins on serial status. Okay, so you'll notice here that they're also publishing these three messages on interprocess as well. And that's the default because it's useful for logging. So if you were to run Goby logger, then you would, without having to do any more work, log the IO data status and serial status messages over interprocess. Let's say we didn't need that. We don't care about logging directly the raw data. You can change that by changing the second two template parameters to IOs, the serial thread line base. So if I change the defaults, the next two template parameters are the layer I want to publish on, a layer I want my thread to publish on, and the layer I want my thread to subscribe on. So if I change these both to the inter-thread layer, then my serial thread will only publish and subscribe on interthread, which is all we're actually using right now. So if I change that and rebuild it, we'll end up seeing this change as soon as it's done building to reflect that. And so I'm trying to make it clear here that the Goby Clang tool is directly reading off the code. So changes you make in the code to affect the publish subscribe architecture will be immediately reflected in the figures you're generating using that tool. So you're never going to have a documentation rot issue where the documentation that you're writing, if you're using this tool, will always reflect what's actually in the code, which can be, I think, quite valuable. All right, so that's rebuilt. Now you can see everything's the same, except it no longer publishes anything on interprocess from the serial thread. So the same messages that we had before, but just all on interthread rather than interprocess. Okay, so that's, let's leave serial behind for a second and talk about TCP. So let's say our GPS was connected, instead of on a serial port, is connected to some remote server, which then reserves the data as a TCP server. And this is a pretty common scenario if you want to feed sensors across to something longer than a RS-232 cable. So we're going to, the same protocol, NMEA 183, but instead of serial, it's a TCP. So it's pretty easy to add support for TCP to our driver here. So we'll just add the appropriate configuration that we need. So let's go over here, wherever my config.proto is for my GPS driver. We'll add the appropriate import for the TCP config, and we'll add a TCP client TCP client config. Now I can't make these both required because I just want to connect to one or the other. So I'll make this a protobuf 10 field, which is basically you need to define, you can't define more than one of these. And so then that replaces the required or optional. It says, so you can either declare, you can either have serial or you can have TCP client, but you can't have both. So then within our application, we can go and add the appropriate header for the serial or the TCP client, the line-based TCP client. So analogous to the serial one. And everything should look very much the same. So we'll have our TCP thread, which is looking identical to the serial thread, except we've got TCP client line-based instead of serial thread line-based, but otherwise the same groups and the same layers we're going to publish on and subscribe on. So then now we have to decide which of these two threads we're going to launch. So if our configuration file has configuration for serial, we'll launch the serial thread. If it has configuration for the TCP client, we'll launch that one instead. And since one of doesn't require that either of these be specified, we'll enforce that here by saying that if neither of these are specified, we'll put out a fatal error and say, okay, you gotta specify one of these. So there we go. Now we have an option between launching the serial or the TCP client version. So that's building. Let's get our GPS connected over a serial to TCP proxy. So we'll use the SOCAT tool for that. So if I run SOCAT with these parameters, this basically says open this file or serial port at 4800 baud and then serve it on this TCP port 54321. So now, I wouldn't do this if it was really connected to my computer. I'd probably just read the serial port, but this would be useful if this GPS was over some network somewhere removed from me. Okay, so that's built. So I can run my Goby3 again, and instead of connecting to the serial, we'll just have the TCP client configuration, and that's going to look like a remote address, which isn't all that remote right now, but it's still server, and we have a port of 54321 and same otherwise parameters. So if I run that, it's like this bigger. You can see we're basically seeing exactly what we saw before, but now we have this TCP client connected to 54321 on localhost. The data streaming in identical, except we have metadata for the source and dest endpoints. So pretty much exactly the same, and that's the idea behind the design of all these IO threads, is that they're pretty much swappable. And if we go back to the interfaces file that we had been building up here, now instead of just the serial thread, we've got a TCP client thread as well. And of course, the Goby Clang tool, since it's a static tool, doesn't know which of these we're going to run because we passed that in at runtime, so it just shows both. So if you look at these messages, the only thing that's sort of missing on the TCP side is the serial command message and the serial status. So those are not over here, and that's because these are specific to a serial port, RTS, DTR. What's different over here is we have a TCP client event, and this will tell us things like connect, disconnect information. All right, so now we've done TCP connection, serial connection to the raw GPS. Let's take a look at using the Goby GPS binary or application. So as I mentioned during the first day, briefly, this is a client for the sort of third-party open source project GPSD. And GPSD, if you're not familiar with it, can connect to any number of GPS devices over a number of different methods, serial, UDP, and a variety of other things. And so you can connect other clients to GPSD. A really common one is like NTP or CronyD for time synchronization for your system clock. So you may have NTP connected to GPSD, and we also want to connect Goby to GPSD. And this makes it a nice, easy way to share your GPS against across several non-Goby clients, perhaps. So if we, the first thing we need to do is add that to the configuration file for GPSD, which is in Ubuntu, it's etc default GPSD. You just put your devices in here, and I've already added USB 0. The other thing you need to do is give GPSD permission to read it. And so in Ubuntu, I have to change the ownership to a user called GPSD. And I'll restart GPSD now. It should hopefully be happy. We can check that GPSD is working with this. There's a GPS Mon client that ships with it that you can look at. And this is sort of a terminal GUI for the GPS. And I see the GPSD streaming in these sentences. It's got latitude, longitude, all this data, 3 satellites. I had 8 yesterday. Must be the clouds. Anyway, so GPSD is working fine. And so we can connect Goby up to it now. So we do that by running Goby GPS. I'll just do debug 1 verbosity, so we'll see a bit more. And you can filter off, if you have several devices, you can choose to just connect to one of them. So this is it's connected to GPSD, but then it's served with the same name as a serial port. So if I do that, I get all this debug information from Goby GPS, and this is just a copy of the messages it's publishing. So it's publishing 2, right now we have 2 different types of messages. So the Goby GPS publications, or we've got this TPV, which is and these are directly what GPSD calls them. So if you want more information, you can look in their documentation as well. So this TPV is the time, position, velocity message. And as it promises, you've got things like the time, the position, and the velocity. And that's the one we often are interested in. The other one is the sky view or sky message, which has got all the satellite data in it. You can see the satellite information if you want that. So let's add to our GPS driver a third option. Then this third option is going to be, if you don't want to connect directly to the GPS, we can use GPSD, and this driver will subscribe to the messages coming from Goby GPS. And if we do that, we'll go over back to our app. We add a third option here. So if our configuration is use GPSD, we'll subscribe to GPSD. So GPSD uses the set of groups in Goby middleware header first. Let's do that. Let's go up here. Gotta add the headers. We need the groups that GPSD, or rather Goby GPS uses, and the messages that Goby GPS uses. And then we subscribe to those. The one that we want is, let's just say we want the position of the vehicle, the latitude, longitude. We can subscribe to the TPV message. And when we get that, it's going to be of the type Goby middleware protobuf GPSD time, position, velocity. I'll call that TPV. And when we get that, normally we would say add this to our vehicle status message, or whatever we actually wanted to do with the position. But for this example, we're just going to, like all the other things, write it out to the screen. So the time, I'll just print out the time as a date using boost POSIX time, and the location using the short debug string in protobuf. And so we'll either connect directly to our serial TCP connection, or we can, if we're running Goby GPS, we'll subscribe to the message coming off of Goby GPS. And the last thing I need to do is just improve my error message here. So I can tell people those are the three options. So let's build this, give it a whirl. Okay, so over here we need to do, we need a Goby3. We need to run our Goby GPS that we were just running, but I don't need that to be in verbose mode anymore. And we'll run our driver. With GPS too. And then, as expected, we're subscribed to these TPV messages, and I'm just writing out the time as a date and the location, the latitude and longitude. And this is where I am. So you can come visit me at my house. All right. So given that, let's look one last time at this this GPS interfaces file. So I've added this subscription, and I'm going to improve the deployment by adding that extra message, or rather Goby GPS that I was added to that deployment. So if we go back to this deployment file, we're going to have the second Goby GPS interface. This is the interfaces for Goby GPS. And if I just rebuild that and look again at this graph, so now we have our driver, we have our serial thread option, we have our TCP client option, and then there's Goby GPS, which is publishing attitude, Skyview, and TPV, and we're subscribed to the TPV over here. And then Goby GPS's implementation uses TCP client to connect to GPSD. All right, so that's all we're going to do with the GPS. And let's go back to the slides for a minute here and talk a bit about sensor state machines. So for longer term deployments, especially things like moorings, sensor lifecycle management becomes especially important for power and data management. Like, we don't need to log all the time. The science mission doesn't necessarily require it, and we don't have the power to do so. So you need to manage the life cycle of, is the sensor powered on or off? If it's on, is the sensor logging or not logging? Is the sensor sleeping? Is it in low power mode? Is it in full power and ready to log? And then once you sort of have a sense of what the sensor is doing, you might want to look also at what the data that are coming off of there are, to keep track of this. Is the sensor providing you with valid data or invalid data based on some potential initial quality control decisions? And so given the often poor implementation of these sensor interfaces, it's correctly and accurately tracking these states becomes a major role of the payload software, or in the case of what we're doing, the Goby software. So a quick look at a real project I worked on, the state machine for controlling the sensors for this. You know, this whole initialize sequence, and then it goes into turning off the sensors until it's time for them to log. You have to turn them on, you have to power on the port that it's connected to, wait for a prompt from the sensor, configure the sensor, start it logging, and then finally you're actually logging. And then when you're done logging, you're going to undo this whole thing, stop logging, sleep the sensor, power off the whole port, and then go into standby. So We're not going to dig into something this complicated today, but we'll look at a simplified version of it. So instead of that, we'll take the sort of key elements, the start logging, we're logging, stop logging, and then sleep. And I think we'll take a 5-minute break now. But after the break, we'll go back to the code, start filling this out, and then you'll finish the last pieces during the homework, which should be pretty clear at that point. So let's come back at about 5 of, a 5-minute break, and then we'll dig into this. If you have any questions, feel free to post them on Slack. Should be able to get to them at the end of the lecture, not before. All right. Welcome back, everyone. So just before the break, we're taking a look at starting to implement this sensor state machine. So if we look at this diagram that I had shown you in the slides, we're going to look at implementing this set of states for our sensor logging. So to start logging, it's logging, stop logging, and then sleep and resume. So we'll do this in the context of the homework assignment, the upcoming homework assignment, and that's going to be involve writing a simulator and the driver for a CTD, and that's a conductivity for which we calculate salinity, temperature, and depth from pressure measurement instrument. Very common oceanographic instrument, as you know. So to do this driver, we'll again go into the pattern directory and copy our multi-thread pattern. So we're going to need to have a serial driver or serial thread in our driver. So we'll copy this to a directory called CTD. And I think you've gotten the hang of this by now, so I'm not going to belabor the point, but just get this code good, ready for us to use. Call the CTD driver, and we'll call the binary CTD driver, and again the config CTD driver. And we don't need these timer threads. We will leave the loop method, the sub A, sub B threads examples, and I'll launch those, clear out the loop example, and that. All right, so we got rid of all the example code we're not going to use, and we're left with just a multi-thread application with a loop method. If I got all that right, build. So how are we going to do this state machine? So we're going to show how to use Boost State Chart. Along with Goby. So I'll show you how to integrate this. And so I think it's very handy. There's quite a bit of code we write for vehicles involves state machines, and formalizing that rather than using if-else statements or enum switch cases can be valuable as your projects grow. And so Boost State Chart, for those of us who are not familiar with it, this uses classes to represent states. And this has a nice mapping. The constructor is the entry action, and destructor, the exit action. And by this kind of design, it allows it to fairly easily add and remove states, because I could just stick another state in between these two. And I don't have to rejigger an entire table, those kind of table-driven state machines or anything like that. So let's start defining our state machine here, these 4 state machine in Boost State Chart. So to do that, we'll go into our CTD directory and we'll create a new header. We'll just call it machine, we'll store the state machine. And we'll lay out some, we'll just include some headers out of Boost State Chart, the events, the states, the machine itself, and transitions. So we're going to need all these. So I'll lay these out now. And the list from Boost MTL, which is used to define multiple transitions out of a given state. We're not going to have multiple transitions. We're only going to have one. As you can see, a single error out of these states, but I'd show you how it would be done so you could extend it to have, say, 2 different ways out of a given state. So then once we have these headers, we can start declaring our state machine. So I'll put it in the namespace Goby3 course state chart just to keep things tidy. And then within there, I need to pre-declare each of the states because they're used by each other. You'll see that in a minute. So I'll pre-declare the actual machine, and then I'll declare the states. Start logging, logging, stop logging, and sleep. So those are our 4 states and the overarching machine, which you can think as wrapping in this whole thing. Okay, now that we've got those pre-declared, I'll add the Goby logger header because we're going to use it, the debug logger, and then we can start defining our machine. So that's the first one we need to do, is define the machine, and this is a subclass of Boost state chart state machine. And the template parameters are the derived class state machine, and this is the paradigm referred to often as the curiously recurring template pattern, which is a type of static polymorphism. So using templates for polymorphism instead of regular runtime inheritance. And start logging, which is the entry state. So when I go into my machine, I go into start logging. So this is where I define where this entry arrow goes. And then we've got a constructor, and I'm going to pass in a reference to the underlying app CTD driver. And we're going to have this because I want my states to be able to publish and subscribe messages in a minute. So we'll store that in a local variable called app. And in order to do this, I need to pre-declare the CTD driver class. So that's my basic machine. Not much other than really storing a copy of the app and specifying the entry state. And I'll start with my first state, which is start logging. And this inherits, shockingly, from a class called state. And this has a very similar set of template parameters. You have start logging, which is passing yourself to your base class, this curious recurring template pattern again, and then CTD state machine, which is the parent, either state or machine. So you can create hierarchical state machines, which have child states, which we're not doing here, but if you had that, this would be your parent state, or in this case, the machine itself. And then we have, I'm going to use this type def to shorten things up a little bit, just to take our base class here. And call it state base, because I'm going to need it in a few places here. There's this context that I have to pass to my base class, which is in the documentation for Boost state chart. That's how it's implemented. And then this constructor, as I mentioned a minute ago, is the entry action. So we'll just write that we're entering the state here. And then the destructor is the exit action. So when I call the destructor, I'll say I'm leaving the state. So it's kind of minimal implementation of a state here. Entry, exit. Then the rest of these are all going to look the same for now. We got to define all the rest of our states here. Just put the shells. The shells, we've got logging is also Boost state chart state. Also the parent is the machine, logging, entry, exit, and similarly for the remaining 2 states. So let's go back now that we've defined our states to our app and add in what we need to use this machine. So I need to include this header. And then we're going to look at, we'll use 2 other virtual classes that multi-thread application provides: initialize, which is called just after the constructor, and finalize, which is called just before the destructor. And that's useful in cases where I want to say pass the CTD driver itself to something within it. Because if your this, if you will, is not valid until your constructor is complete. So if we do that here, we can pass a fully valid this reference to the machine. And then we call initiate. I should actually declare my machine. So I'm just using a pointer to the machine. The pointer just lets me set it later rather than in the constructor. And then in finalize, we'll just do the inverse. There's terminate, which is the boost state chart clean up and quit the machine. And to keep things tidy, I'll just clear out the pointer as well. So now that we've done that, we've basically built this, which is to say a bunch of states with no transitions. Actually, we kind of have this, as we've declared where we're going to start our machine, but not anything else. So this blobular, not quite our state machine. So what are we missing? We're missing the transitions between states. And in boost state chart, transitions are driven by events. And the events are just another class in boost state chart. So let's create some events and put them into our machine. So let's call our events. We'll have the event logging started goes us from start logging to logging. The event do stop logging goes from logging to stop logging. The event enter sleep brings it into sleep, and then again do start logging gets it logging again. So those are our events. And to define the events in code, we have I just stick them up near the top. They need to be declared before you use them, but no particular order they need to be. So the events are also struct ev do start logging, and this is just a convention and prefix them with ev. You don't have to. It makes it clear. You can put them in different namespace would be another option. Boost state chart event, and again the curiously recurring template pattern that is used all over the place in boost state chart, as well as in Goby and a number of implementations. So that's the events at a minimum are just an empty struct. You could put data in them if you wanted to pass data between your states. And then the rest of the events look the same. Logging started, stop logging, enter sleep, all subclasses of event. Okay, now that I've got these events, I need to put the transitions into the states. So the transitions are done by declaring a list of reactions. So each state can have a list of reactions, and these reactions are reactions to a particular event. So you can do things other than transition between states, which I won't show you here. But in our case, we want to react to an event by transitioning from one state to the next, and that's defined as type def. And I'm using type def instead of using here because that's where you'll see it in the documentation for boost state chart. It's the same thing basically. So what we want to do is when we get we want to transition when we get EV logging started. We want to transition to the state logging. So, and then as I mentioned, you can have multiple reactions or transitions of any type within a state. So we just have one. So this is a list of link one, but you could have a common delimited list of other transitions or other reactions there. So this is the when we're in start logging and we get EV logging started, we want to transition to logging. And the rest of the states follow an identical model. So in logging, when we do stop logging, we want to go to stop logging. When we're in stop logging, when we get enter sleep, we want to go to sleep. And finally in sleep, when we get to start logging, we're going to start logging. So now our state machine looks like this. And now that I think about it on designing this, maybe I've decided it makes more sense to put our machine straight into sleep rather than into start logging, because my sensor, when I power it on, enters into sleep. You know, who knows? We'll just assume that's the case. So let's say we want to turn it into this. It's straightforward matter then of changing the entry state of the machine. Change this to sleep, and now that's the entry state will be sleep. Okay, so now that we've got this, just build it to make sure I didn't make any typos. We might want to know from the main thread of this application, the Goby side, we might want what state the machine is in. This is pretty common, so that we can report it out to the system, we can log it, and things like that. So to do that, we'll use publish subscribe, because why not? That's what we're doing all week. And so to do that, we need to declare a group that we're going to publish this on. It should start becoming pretty second nature by now. And because I'm going to use this group just inside of this application, I'll declare it here rather than in the group's header. You could put it there if you wanted to too, but this keeps it more locally scoped since I never intend to publish this on interprocess. And then within, I'll create a function that the states can call. And we're going to call it publish entry. So this function was going to be called in the entry of each of the states to publish to interthread. And I'll work through this in a moment more. To the group state entry, the name of the state as a string, and then the other stuff you're seeing here is the states are run in the same thread actually as the main thread. So if we publish something in the same thread, we don't by default receive it ourselves. There's no loop back, if you will. But if I set echo of true, then every publication within a thread is also received by a subscription in that thread. And we're going to do this so that we can pass things in and out of the machine, even though they're running in the same thread. So that's why this is here. And getting access to the interthread publication portal is through state outermost context. That gives me the machine itself. And then inside of the machine, I kept a reference to the CTD driver app, which I can call interthread to access a reference to the interthread portal. So that's a mouthful, but ultimately this is just a handful of a handy function to publish the string name of our state on interthread. So how we're going to use this is inside of each of the states. We'll replace that with publish when I enter the state. The state name is start logging as a string, and I need to pass a reference to the state so that I can actually get to things like the machine and whatnot. And then we also, so interthread here, this method is protected. So in order to call it from outside of the CTD driver class, we need to add a friend function. So we're just going to say publish entry can call our protected and private methods. So now that we've got that publication, we can add the matching subscription. So over here in the main thread, we can subscribe to that same state entry, which is just a string that we're publishing. So when we get that string, we'll just write out to glog that we entered the state. But now we have access to the information of what state we're in over here. Okay, so now that we've got this, we can add this to all of our other states. And we'll make this complete by adding an equivalent publish exit. So this is exactly the same, except we're publishing it on a different group called state exit. This publish exit function. And then we can add publish exit to all of our states as well. I should mention this isn't the only way you could handle keeping track of the state information, but it's a nice use of the publish subscribe architecture to do so. And back over here in our app, we're going to want to subscribe to that, as well as declare publish exit as a friend. And the subscription will look the mirror image. Okay, so now I've got publishing when I enter a state and when I exit a state, and I'm subscribing to the entry and exit groups over here and just writing out when we enter and exit a particular state. So the last thing that remains before we can use our state machine is actually to trigger some of these events. So right now it'll go into sleep and just stay there. And we'll start by just testing this out. We're gonna, every time we go into loop, I'm gonna run loop at 1 hertz so that it's not insanely fast. 1 hertz instead of 10. This is totally just to test our state machine. We're gonna take the, we're gonna keep track of the current state as a class private variable. And when we enter the state, we're gonna keep track of what that state is when we get an entry to the state. And then within loop, we're just gonna, every time we enter loop, we'll just trigger the event for the next state. So when I go into loop and we happen to be in sleep, we'll trigger the event, do start logging. If we happen to be in start logging when we enter loop, we'll trigger the event logging started. So this is just going to 1 second walk ourselves through the state machine 1 step at a time. And this is just tested, obviously, and we'll pull these out as we continue on to something that's much more realistic. This is my lambda capture this because I'm storing a class variable. So I should mention, in a real system, instead of the strings here, I would use enumerations, because then you can pass those on. You can, publish them cheaper, and you don't have to worry about typos. But for this simple example, I'm okay using the string names. All right. Let's clean this up a little bit. Oh, we got Goby3 as always, and then our CTD driver. I'll use debug 2 so I can see what's going on here. All right, so we entered the machine, we entered sleep as expected. And then the next time we entered loop a second later, we trigger this do logging event, which exits sleep and enters start logging. The next second, we do EV logging started. The next time we enter the loop, we leave start logging and enter logging, and so on and so forth ad nauseum through this entire state machine. All right, so let's do something with this now rather than play little games and loop around this forever. So let's look at the interface for our CTD, which is going to be based on NMEA 0183. And this would be, provided to you by the sensor manufacturer. We're going to make one up for the core purpose of this course, but it's not wildly different than something you might see for a real system. So it's going to be an RS-232 9600 baud serial device. A little right arrow means a message from the computer to the CTD, and the left arrow means a message from the CTD to the computer. And there's going to be a checksum, a standard checksum at the end of each message. So I want to wake up my CTD. I send this command wake, and then the CTD acts it with an ack wake. I want to start logging. I send this command start, and the CTD will act with start. And once it's logging, it'll stream data with the DAT message at 1 hertz with salinity, temperature, and depth. And then once we want to stop logging, we send the stop command. Again, it acts it. And finally, there's a sleep. You can send sleep. It'll go into a low power mode. So this is like a simplified version of something that isn't too far off from what you'd see with a real sensor. So given this, let's add serial thread to our driver. So now we're going to add, this is exactly what we did earlier with the GPS. We'll include the header for the line-based serial. This is our carriage return new line delimited ASCII messages. And in the constructor, we will declare a serial thread and some groups that I'll add in a minute here and launch that serial thread. So again, exactly what we did with the GPS. So in the config, we got to add a configuration for where our serial is connected to with the appropriate header for that. And in the groups header, we'll add our pair of analogous groups for the CTD. Okay, so once we've got all that, we've got the groups. We're going to publish this. We'll just keep it on interthread. This could leave this as interprocess if you wanted to log the raw data directly. Okay, so let's subscribe to the IO data and actually parse the NMEA messages that are coming across from the CTD. So to do that, we'll use another class in Goby, the NMEA sentence class, which is an automatic parser and assembly for NMEA 0183 messages. And let's create a function that's called handle incoming serial. Every time we get a serial message, we'll call this, and it's we'll provide it the NMEA sentence class, which is the one that parses our sentences for us. So then in our constructor here for the CTD driver, we'll subscribe to the CTD in. So again, this is exactly what we did with the GPS. And the type of message is going to be the IO data that comes from all of the IO threads. And then when we get this IO data, what we'll do with it is try to parse it into an NMEA sentence. So we'll do a try catch here because the NMEA sentence will throw an exception if it doesn't parse correctly, like there's a syntax error or missing checksum or wrong checksum. So we'll have Goby util NMEA sentence, we'll just call it NMEA, construct it with the string that comes across from the serial thread, and we'll tell it that we want to validate the checksum if one exists. And then once we've parsed this, we can call the handle incoming serial function I just declared. And the NMEA sentence can throw a bad NMEA sentence exception if there's a problem with the message. And in this case, we'll just write a warning to the log and continue on if we get a bad sentence for this example. So the last thing is going to be to declare this handle incoming serial function. And at the moment, we'll just write the string representation of the NMEA sentence back to the screen. We'll do more of this in a moment. So let's build this, see if we got it right, and then set up the test run of this. Okay, so while that's building, we can go over here, and we're going to use SOCAT with a pseudo terminal connected to standard in, standard out. So this says connects my pseudo terminal with the name of temp CTD to dash, which is the in and out, what I type here. So anything I type into here will get sent over this pseudo terminal, and anything that comes out of that pseudo terminal will get just displayed right here on my screen. My CTD driver has been building it. There we go. Okay, cool. So that's done. And so we can run my, we need a Goby3, and we can run Goby3 course CTD driver. Do debug one verbosity for now. Connect to the serial port in this the pseudo terminal port that I just created over with SOCAT. The baud doesn't really matter for pseudo terminals, but we'll give it 9600. Okay, so connected to the serial port, and then if I type something in here like ccac wake, so I'm now being the sensor, if you will. You see it shows up over here as well as in our main thread here. And I had intended to at some point, yes, I missed adding a new group here, glog, to cleanly display this in a separate window in the incursive GUI, but not a big deal. So we see ZC wake, whatever I type over here. So I'm simulating the CTD right now the most primitive way possible, which is typing into the terminal window. Okay. So now let's begin the process of actually using our driver. So we're going to take the start logging and stop logging transitions out of loop and move them into the response to the incoming messages. So when we get an ACK for start, we're going to want to go out of start logging and report that logging has started. Let's go up here. So when we get an ACK for our start command, we'll say, okay, event logging has started, and we'll go into logging. And when we get an ACK for our stop logging, we'll enter sleep. So what that looks like here is just the sentence ID, which is the second 3 characters of the NMEA sentence, so CMD or ACK. And if the size of, so the NMEA sentence is a vector basically of all the parts. So this would be 0, 1, 2, 3, or whatever. So we want to make sure that this is at least has a second message so that we don't read off the end of the vector. And if that's the case and it's start, we'll trigger the logging started event. So we've ACK start, and if the ACK is for stop, we'll enter sleep. So that's this transition and this transition driven off of our actual sensor. The other part of this is going to be to actually send the start and stop commands and the entries of those respective states. So if we go into our machine here and We're going to need to include a couple more headers and include the MIA sentence here because we're going to use it. And we'll also include the groups so that we get access to the CTD in and out groups. So then we'll create another free function here, like our publish entry, publish exit, same idea. Just now we're going to publish CTD out, which is data of the MIA sentence type to our CTD. And then we publish this to the CTD out group, which if you go all the way back to when we were learning about the GPS, that's messages from any of the other threads over to the IO thread, and then that gets sent out, in this case, a serial port. All right, so we got this publish CTD out, and in the constructor for start logging, so when we enter start logging, we want to publish a command to actually start logging. And so we'll create an EMEA sentence of the ZC command start, and then call publish CTD out, which publishes it over to the serial thread, which then actually writes it out the serial port. And similarly, in stop logging, we want to send ZC command stop. And for completeness, we'll also add sleep in here. When we enter sleep, we'll call ZC command sleep. The last thing we need to do before we can build this is add this third function as a friend so that it can access interthread and publish. So now that we've done this, we've removed half of our fake state transitions, if you will, that are happening on 1 Hertz and loop, and made them now driven from the command ACK response, call response. Okay, so that's built. We can go back over here. We can rerun everything. And now if I, so now that I enter start logging, my driver sent the command to start logging and it's waiting for the response. So I will be the CTD for the moment and ACK the start command. So it gets the ACK and enters logging. And then the next time it went into loop, it immediately triggered stop logging and told me I want to stop. So I'll just do ZC ACK stop. And then goes back into start, so on and so forth, over and over again. So there's a couple cleanups I'm going to do before we move to removing those last 2 fake transitions in loop, which is I want to avoid the state machines starting before the serial ports actually open and ready so that the CTD doesn't miss the first command that we send, in this case, the start command. So we'll move the machine start out of initialize and in response instead to the IO status message. So put the code in here and then we'll look at it. So we're going to subscribe to IO status from the CTD in, so our driver. And when we receive that the link is open, well, then it'll start our machine. And if the link isn't open, if it's closed or an error, we'll terminate our machine. And so those are the sort of the 2. It'll drive it instead of when our app starts up and closes. We'll go off of when the serial port is ready. And with a real sensor, you're probably also going to have to use a timeout and retry model, because sometimes the instrument isn't going to respond to your first attempt, but we'll ignore that for this course. And it's something you'll have to figure out when you do this for real, depending on how cranky your sensor is. So now we need a control message to get these last 2 messages out of loop. So somebody outside of the driver is going to decide we want to start logging and we want to stop logging. Either a scheduler, autonomy system that decides it's time to collect data, or whatever it happens to be. But as far as our driver is concerned, we need a control message, and it's going to be published by some external entity, like a scheduler. So we have a CTD control group for that, publishing that message. We'll go into src lib messages, define ourselves a new protobuf message, put it in ctd.proto, and we'll call this ctd control. Desired state, do we want our CTD to be logging or not logging, and send that. So really simple little protobuf message. Make sure that we actually build the proto message. And then we can use it inside of our application. So if we now go to subscribe for that, we can inter-process subscribe our control message and call the events based on the contents. So we subscribe to the control message. Yeah, you'll know about it soon enough. We subscribe to the control message. If the desired state is logging, we'll send the event start logging. And if the desired state's not logging, we'll send the event stop logging. And so then we can clear out our loop method entirely. So everything is either driven, the state machine is either driven by the external control message or by the start stop response of the CTD itself. So now it's truly event driven rather than in this loop method. So while this is building, I would also mention that if you send an event that's not used by a particular state, yeah, I'm going to include the header, don't I? Details. The whole thing. So what I was saying is if you send an event that's not in the transition first state, it's just ignored. So if I'm already logging and I get UV logging started, nothing happens. And that's usually what you want. So if we send the command to start logging or logging state desired and already logging, then this is silently ignored by our driver. All right, so now that's done building. Well, that's finishing building. We can get set up to launch this. So we're going to add this to the trail example. So if we go into launch trail config templates, we can add a new configuration block for our CTD driver. And if you, so remember from the homework, the configuration preprocessor will fill out our app and interprocess blocks for us. And then we just need to define the serial config, which we'll just keep using the same temp CTD PTY for now, as we were doing a moment ago. And then we have to add this to the, so we're going to add this to the AUV. So we're going to put the CTDs on our AUV. So we'll add to the AUV preprocessor script that we want to be able to generate configuration for the CTD driver. So the same template substitution stuff you've been seeing all week. So now that we've got that all set and our code is built, head built. Cool. Then we can go back over here and actually, first thing I have to add it to the launch file as well. So the last thing I forgot to do is add it to launch for AUV.launch. So we want to launch our CTD driver, and I'll keep it in debug 2 verbosity for now so that we can still see what's going on. And I wanted to be able to send the CTD control message. So we'll go in liaison, we'll send it as a command from liaison. So just like we did for the USV command, except instead of sending it on inter-vehicle layer, we're going to publish it just on this vehicle. So we're pretending to be the scheduler, whatever is going to start and stop the CTD for now. All right, so we got all those things. We can go back over to the code or the command line. We can restart a little SOCAT simulator for now. And we can kick off our vehicles. So we go to Goby3 course, launch trail. We'll just run a single AUV. And got all that running, and I can reattach the screen session to my AUV CTD driver. So this is exactly what we're seeing. So now it's just going to go straight into sleep. And if I open my commander here, I've got the CTD control message. I can send that I want my CTD to be logging. If I send that logging message, it goes into start logging, sends the logging command. I'll be the simulator and send ZCAC start. And now it goes into logging. Similarly, if I send not logging, it's going to send the stop command. And as the simulator, I can send stop. And so now kind of the only piece that's missing is the simulator, as I'm not going to sit here all day and test my vehicle by typing ZCAC start and stop. So that's the next piece. And the last piece we'll look at here is simulators. And given the time, I'm going to move some of this over to the homework, but in terms of implementation, so you can read through the rest of the course notes to get started on that. But I want to mention a couple of sort of best practices about simulators specifically. So the key goals as I see them are to replicate, let's go back to the whiteboard here. We want to replicate the real behavior, and I'd say, and the API where possible of the sensor. Because the behavior is important for the rest of the system and autonomy. And the API is important to getting your drivers right, because the last thing you want to do on your expensive cruise is to spend it all debugging your CTD driver. So if you can write a simulator that mimics the API, at least the part that you need, you can solve a lot of easy to fix headache in your simulation time rather than push it off to pre-cruise and cruise debugging. And because we all have limited amount of time, you really want to start off by capturing whatever the key behavior is. So don't worry about implementing everything that's in the entire spec sheet for the sensor. That's probably 100 pages long. So start off by that, get it working, and then you'll realize pretty quickly when you start using it what the sensor quirks and flukes are, and that's useful to build that into your simulator as well. So that, and the same reason that unit testing should be, if you find a bug, add it to the unit test, demonstrate that it breaks, and then fix it and demonstrate that it works. You want to do the same thing here with your simulator. If you find a bug in the real sensor's interface or a fluke in it, ideally you want to add it to your simulator, show that it breaks your driver, fix your driver, and show that it works with your new sort of featured simulator, and then also with the real instrument. So there's a sort of iterative process, and then iterate that you want to do, because that's going to give you the most bang for your buck out of your simulators. So in the homework, I'll have you work through the rest of the lecture notes here that create the stub for the simulator. It's nothing you haven't seen before. You're just going to create a standalone application, open up a pseudo terminal like we do here in SOCAT, except using the pseudo terminal thread in Goby, which is pretty much the same as the serial thread from a usage standpoint. And then once you have that, you can fill out the rest of the features. And in the homework, we'll also send these messages up to the USV, which will aggregate them. We can log them and display the figures of our data after the mission is over. So it's pretty neat little assignment if you get the chance to finish it. So in the last 15 minutes or so of this lecture, I want to sort of wrap up the week. And we'll do that by switching back to the slides here. And so, wrapping up everything we did this week, there's a lot to look at, a lot of code, a lot of different features, and there's still a lot to be done though. And so I wanted to give you guys a view of where I think Goby's going, at least what's on my mind, because I think this could be helpful. I'd love some feedback, and especially love anyone who wants to become a contributor to the project, because I think we can work together to build something pretty neat here. So the official release 3 will be very soon. I didn't get time to totally tidy it up before the course, but not long. And then once that's done, sort of looking at what's coming on the horizon. Something I specifically are interested in is when I've got multiple modems connected to my vehicle, how do I prioritize the data flow from that? So I can envision having an AUV with a Wi-Fi connection and an acoustic modem. And when I'm on the surface, I want to send things over Wi-Fi if I'm connected to my subscribers. And if I'm underwater, I have to send it over ACOMs. And so the flood method would be send it over all of them. Or I could have some sort of priority thing, which is what I was just mentioning, like if Wi-Fi is connected, use it. If it's not, use acoustics, things like that. Also want to add to the driver catalog, support more modems and vehicles that goes along, sort of expand the usable reach of the project. There's, I think, a fair amount of interest out there for some version of the Moose Gateway for ROS. And I think that could be something that would be nice to have. I also would like to be able to use Moose IVP without having to use MooseDB. There's some thought maybe of taking the core of Moose and figuring out how to bring that into Goby more natively while still using as much as possible in terms of behaviors and core algorithm code from the IVP project. And the last two are like expanding the implementations available for the interprocess layer. So 0MQ is an option. Is it the best option or the only option? No, necessarily. There's the boost interprocess. I was having a discussion yesterday with folks about that. Let's use a shared memory, as it might be a nice alternative implementation. And then supporting some more messages some new marshalling schemes that I think are kind of fun. Captain Proto is one that's written by the guy who did Protobuf 2 at Google, and then he left and did his own thing. And there's Message Pack, which is kind of appealing, perhaps. JSON's one that definitely should support, probably, and so on. And these will sort of evolve as there's a need. So there's this course as one of the resources available for Goby3, but of course, that's not it. So I want to just summarize the main resources that are out on the internet for getting used to using Goby or contributing back. There's the main developer manual, which is built using Doxygen and Markdown, and that's at goby.software. There's a source code on GitHub. I release packages for every release and on the daily build of the 3.0 main branch for all the LTS versions of Ubuntu and the 2 newest Debians at any given point in time. And these are hosted on my server, but the instructions on how to add those to your app sources list is in this developer manual. And there's a wiki. It doesn't have a whole lot in it, but there's some decent stuff you can poke around, and you want to add to that, could be nice. And the examples repo with Goby3 examples, which this course covers a fair number of things that are in there, but not in exactly the same way. So you may find these examples useful to look into as well. So here's my somewhat of a push for you to contribute. So I know there's an interest in people to contribute to the project, and sometimes it's a little bit daunting to be like, where do I start? So these are my suggestions of ways you can contribute. Some of them are fairly easy. New modem drivers, I think that's been the main way I've had people contribute actual significant pieces of code at this point in time. If you have a modem that you want to use with Goby, write it, and I'd love if it could become part of the open source project. If you're using an existing modem that's one of the drivers and you feel like it needs to be updated or whatnot, if you want to adopt it and become the maintainer for that driver, that would be awesome. And let me know. Then the same thing for the front seat interfaces. New vehicles or adopt existing drivers. And another way is if you find something you feel is missing in the examples project that you feel like could use a simple like equivalent of the little apps we've been building for this class to demonstrate how something's used. Especially if you find you have to write it yourself to figure out what's going on, you know, if you can contribute that back, it could be useful for somebody else. Updating the documentation is very easy. So if you find that you want to contribute to that, it's in Markdown, it's in the Git repo for the project. So if you find you're you know, writing your own notes and you think that somebody else would benefit from this information because it's just not there, consider contributing an updated or a new documentation page to the Markdown. So put up a pull request. Basically, the answer to all these is put up a pull request, work through it, and get it in. If you have some other piece of useful code that you want to contribute that you think fits in Goby in some way, pretty broad statement, feel free to suggest contributing it. And the last one is different than all these, the non-technical way. If you're interested in supporting the project, but you're not going to be writing open source code, you can support the project financially. The easiest way is to sponsor it on GitHub, but you want to talk to me, there are other ways. Writing code is not free, and open source code, while useful to everyone, can be sometimes hard to get any one person to want to pay for. So core sponsorship for the project is very useful. And with that, thanks for attending. And thanks again to the sponsors. Appreciate your help getting this course together. Mission Systems, Blue Ocean, and Raytheon. And thanks again to everyone. If you have any questions about today's lecture, you know, you can post them now, or there's definitely few enough us on now. Just unmute yourself and ask if you have anything you want to ask in the last few minutes here. Okay, well, if you come up with anything you want to ask me, I'll be on office hours again for the last time today and on Slack. So here's your chance. And thanks again. Take care.
Thanks, Toby.
Sure thing.
Thank you very
Toby.
much.
That was
Thank you,
excellent.
Toby.
Thank you.
Yeah, thanks.
Appreciate it. Take care.